All right, let's dive into a topic that honestly powers pretty much everything in your digital life. We're talking about multithreading and parallelism, the secret sauce that makes modern computing possible.
I mean, really think about it for a second. Right now, you're watching this, but you probably also have a bunch of browser tabs open, maybe some music playing in the background, notifications popping up. How in the world does one machine juggle all of that without just completely freezing up? Well, that is the big question we're going to tackle today. And to make these pretty complex ideas super simple, we're not even going to talk about computers at first. Nope. We're going to step into the kitchen. We're going to use this simple act of cooking a meal to break it all down.
So here's our game plan, or recipe. We've got 3 main tasks: boil some water, chop up some veggies, and fry the meat. Seems simple enough, right? But how we decide to tackle these jobs, well, that changes everything.
And this is where it gets really clear. On the left, you've got just one cook. That's like a single-threaded process. He has to put the water on the stove, wait for it to boil, then he can start chopping veggies. It's all one step after another. But look at the right. With 3 cooks, you've got multiple threads. One person handles the water, another is on veggie duty, and the third is frying the meat. They're all working at the same time, and no surprise, the meal gets done way, way faster.
Okay, so let's give a name to what a really smart single cook does. That's called concurrency. This is when our cook puts the water on to boil, and instead of just standing there watching it, he switches over to chopping the vegetables. He's not actually doing both at the exact same time, but by rapidly switching between unfinished tasks, he creates the illusion that he is. And this is basically what your computer's operating system is doing all day long. Parallelism, though, that's the real deal. This isn't an illusion. This is when you actually have multiple cooks in the kitchen, or in your computer, multiple processor cores. They are truly, genuinely executing different tasks at the exact same moment. One core is boiling the water while another core is chopping the veggies. That is true simultaneous work.
This chart really pulls it all together. Up top, you've got one core doing one thing at a time. Super simple. Then you see that one core juggling 2 tasks. That's our clever cook. That's concurrency. In the third box, you have 2 cores, each working on its own separate task. That's parallel, sure. But the real magic? It's that bottom box. You've got multiple cores, and each one is juggling multiple tasks. That's concurrency and parallelism working together. That's the engine of modern computing.
Okay, so we've got the big ideas down. Now let's talk about the actual hardware, the tools inside your computer that make all of this happen. Let's talk about cores and threads. So a thread is like the smallest possible to-do list you can give a processor. You see, an application, like your web browser, isn't just one giant task. It's actually made up of dozens of smaller threads all running at once. There's a thread for drawing the buttons and menus, another for loading the web page in the background, and yet another for playing that video. So here's a classic problem. A CPU core is insanely fast, like unbelievably fast. So fast, in fact, that it often has to just stop and wait for slower parts, like your computer's memory, to catch up and send it the data it needs. And in those tiny moments, that incredibly powerful, expensive piece of silicon is just sitting there, doing nothing. What a waste, right?
And that's where a really clever technology called hyperthreading comes into play. On the left, you see the problem. The core does some work, then hits a wall and has to wait. But look at the right. With hyperthreading, that single physical core pretends to be 2 cores. It takes on 2 threads at once. So when thread A has to wait for data, the core doesn't just sit idle, it instantly switches over to thread B and keeps working. It fills in those empty gaps. Now, here's the key thing to remember. Hyperthreading is not magic. It doesn't double the core's power. It's not the same as having 2 real physical cores. But by making sure the core is busy more often, it gives you a really nice performance boost, usually somewhere in the ballpark of 10 to 30%. It's not about more raw power. It's about being smarter with the power you have.
All right, now we have to talk about the 2 main specialists in your machine, because you can't really talk about parallelism without them. This is the CPU versus the GPU. Think of them as 2 totally different kinds of chefs. This table nails the difference. The CPU is your master chef. It only has a few cores, maybe 8, 16, 32, but each one is a genius. They're incredibly powerful and can handle any complex one-off task you throw at them, like managing your whole operating system. The GPU, on the other hand, is an army of line cooks. It has thousands of cores. Now, each individual core is pretty simple and can only do a few things. But when you get thousands of them working together, They can chop a mountain of onions, or more accurately, process millions of pixels, all at the exact same time. So now that we know all the players, the concepts, and the hardware, let's see how this all comes together. Where do these things actually give our devices their superpowers out in the real world? Gaming is the perfect example of this partnership. The CPU, our master chef, is busy handling all the complicated stuff, the game's logic, the physics calculations, the enemy AI, and responding to your mouse and keyboard. At the same time, the GPU, our army of line cooks, is handling one massive, repetitive job, drawing every single thing you see on the screen, from the characters to the lighting and shadows, 60 times a second. And you see the exact same thing in creative work, like video rendering. The CPU acts as the project manager, organizing all the data and managing the timeline. But the heavy lifting, the brutal task of calculating the final color of every single pixel for every single frame of your video, that gets handed off to the GPU's parallel processing army, which slashes render times from hours to minutes. You know, this isn't just about gaming and graphics. The entire internet is built on parallelism. Every time you go to a major website, you're one of maybe thousands of people connecting at that exact moment. The web server's powerful multi-core CPU handles each visitor's request on a separate thread, processing thousands of them in parallel so that everyone gets a fast, smooth experience. So, let's do a quick recap. A thread is just a single to-do list for a processor. Concurrency is smart juggling to create an illusion of doing things at once. Parallelism is actually doing things at once. Hyperthreading is a clever trick to make one core work on two things, and the CPU is your genius master chef while the GPU is your army of specialist line cooks. Got it? Awesome. And so that brings us to the end. For decades, making computers faster has meant making them better at doing things in parallel. But as our games, our AI, and our science demand more and more power, it leaves us with a really big question to chew on. What comes next? What's the next giant leap in computing that will take us beyond the kind of parallelism we know today? Something to think about. Thanks for joining me.